In section 10.3, we will be talking about different type of samples that we are going to take. It's not necessarily that we are doing the hypothesis testing over the what's so-called the independent samples. Sometimes no, we are doing the study maybe over paired samples. Paired samples. What does it mean by paired samples? Let's look at the meaning, then we discuss some of the examples. Samples that are selected in such a way that values in one sample are matched with the values in the second sample for the purpose of controlling for external factors. Another term we call it the dependent samples. Maybe we're going to take one sample of patients, right? And we test their blood pressure. We take the measurements of the blood pressure of this sample. And after that, we take the same sample, we give them a medicine to control the blood pressure. Then we take the blood pressure, we measure the blood pressure again for each of them, and we find the difference. We would like to study the difference. Does the medicine really make changes? Does the medicine make the blood pressure better or no? So this is an example of the paired samples. Another example, a paint manufacturer might be interested in comparing the number of square feet that a new paint mix will cover per gallon with the area for an existing paint mixture. One approach would be to have one random sample of painters apply a gallon of the new paint mixer. A second sample of painters would be given the existing mixer. In both cases, the number of square feet covered by the gallon of paint would be recorded. Now, in this case, the samples would be independent because the area covered by painters using the new mixer would not be in any way affected by the area covered by the painters using the existing mixer. Now, however, we have something important here. This would be a fine way to do the study unless the painters themselves could influence the area that the paint will cover. Maybe we have expert painters. They use different techniques, so they will be able to cover more area with a gallon of paint than other painters, regardless of the type of paint used. These are the external factors that we talked about. Then, if by chance most of these good painters happen to get assigned to the new mix, the results might show that the new mix covers more area, not because it's better paint, but because the painters who used it during the test were better. That's why, to overcome this problem, a company might want to use paired samples. We have a group of painters, the same group. We selected them, and each painter given 1 gallon of each paint mix. 1 gallon from that one, 1 gallon from the other one. Then we measure the area covered by each painter for both paint mixes. Doing this controls for the effect of the painter's ability or technique or skills or experience. So that's why in this case using paired samples is much better using independent samples because we are controlling these external factors. It will not have an effect on the variable that we are studying. So the paired difference is x1 minus x2, D is the difference. X1 is the value that taken from sample 1, x2 is the values that were taken from sample 2. So we find the difference between these two values. We get something we call D, is the paired, we call the paired difference. Also, we can find the average of that value. If you have two samples, x1, x2, we can find the difference between these two values. Then we can find the average of these two values. And this is the point estimate for the population mean. To get the confidence interval, what we have to do is just the point estimate plus or minus the t-value times the standard error. This is the critical value times the confidence level, right? What is the SD? SD is a sample standard deviation, which is this, we use this formula. So to find the confidence interval estimate, we can do this using Minitab. Also, we can do the hypothesis testing. Before we move to that one, the t-test is that value. But the hypothesis testing that we are going to do is, again, we have paired sample. Excuse me. So you have a paired sample. And we use the t-test in this case, and this is the t-test statistic. Again, we will be using the Minitab. And -1 is the difference, is the degree of freedom, and 1 because we are approximating only one value, which is the D. And the D bar is the mean paired difference, and the mu D is the hypothesized population mean paired difference, and so on. Let's look at this example. Suppose an independent test agency wishes to conduct a test to determine whether name brand ink cartridges generate more color pages on average than competing generic ink cartridges. So this is the hypothesis that we are going to do. That the name, this is the claim, the name brand ink generate more color. So the average of this is a mu d, the difference basically. It's a mu of the name generated brand ink. Let's call it a mu NB minus a mu generic ink, generic GI. Let's call this one mu D. Mu D, okay? The difference is mu D. This is greater than 0. This is my H alternative. So again, let me just put that one here. So I just wrote them quickly. So the alternative is we are assuming that the mu D is greater than 0 and the mu D for the null hypothesis is less than or equal to 0. What is mu D? Is the difference between the average of the name brand and the average of the generic or generic cartridges. So these are my hypothesis testing. This is one tail test. And it's a right tail. It's a right tail. So we're going to get something like this. So what did the company do? They took samples. They took samples from each name brand and the generic, right? And they took basically six users. They used both of them, right? And they counted the number of pages. So suppose the test is done using paired samples. This is given to us, paired sample. This means that the same people will be using both type of cartridges, and the pages printed in each case will be recorded. So the first user, he used the name brand. He printed 306. The other one, the same customer or the same user, printed 300 pages using the generic. The second user printed this amount and this amount from two different cartridges. Significance level is 0.01, and we have 6 people who participated. So it's clear that we are doing paired samples, not independent samples, because we have only one sample. They are doing 2 things, right? So we will go to Minitab and show how to solve this. Okay, these are the data that we got from the 6 users. We have the first type and the second type. So what we do, we go to, I'm going to copy these 2 values, by the way, and then go to Minitab, select the 2 columns, paste. So we got the name, brand, and generic. Then we go to statistics, basic. Then I'm going to select not 2 sample t-tests for these are 2 independent samples. We're going to do the paired t-test. Each sample is in a column, yes. So what we are assuming is the name brand is greater than the generic, right? This is the assumption that we made. Options, we have 95%. The hypothesized difference is 0. And what we are saying that the difference is basically greater than 0. Because the alternative hypothesis is that the mu D is greater than the 0. Then we do OK. We click OK. Then we get these values. The estimation for paired difference, we have descriptive statistics. And what we're looking for is the p-value now. The p-value is what? The p-value is 0.079, which is what? Which is greater than 0.05. Greater than 0.05. So we fail to reject the null hypothesis. So there is no sufficient evidence to conclude that the name brand ink cartridges print more pages on average than the generic cartridges. We don't have sufficient evidence to reject these facts. There is no sufficient evidence to conclude that this is true. This one, the second one. We don't have sufficient evidence to say that the name brand ink cartridges print more pages compared to the generic cartridges. Okay, so we fail to reject because the p-value is greater than the what's so-called the alpha value, which is 5%. Okay. Yeah, I just look at the question back. It seems that I use a different alpha. So let me go back again and change the alpha as 99% because it was 1% the alpha. So this is 99% equal. We're still getting the same value, which is, I mean, the p-value is greater than the 5%. It's 7.9%. The conclusion doesn't change. So, yep. So we got the same value already. So this is the conclusion that we made already. By the way, sometimes maybe you can do the following. You can find the difference here. You can find D. Well, there's no need to do this. D equals the difference, this one minus that one. Double click. Then we find the average of the difference, the average. Then you find standard deviation, SD, of this sample, stdev.s. Then we get these values. Then I'm going to copy the D. Let me copy the D. Go to this. Maybe more work, but let me just show it to you. So what we do, we go to stats. Actually, there's no need to copy the D, but let's use the pair test. We can use summarized data, the difference. What's the sample size? 6. What's the sample mean? We calculate that one. 12 point, let me copy it. What's the standard deviation? Is that one. Then we go to options, 99%. All of these are the same, equal, equal. We got the same answer. So either you use the summarized data or we use the column. But summarized data, you have to produce more. You have to give me the difference first, then you have to find the average of the difference, then you have to find the standard deviation of the difference, okay? So both methods give you the same answer. Both methods are correct. So this is everything about the hypothesis testing for the mean. We covered the independent samples and the paired sample.